Hello students, and welcome to the lesson on functions, and we're going to look at a very rigorous definition of some of the concepts relating to functions today. But to start off, a function can be viewed as a machine with input and output. And one of the rules of a function is that every input has exactly one output. And in this video, I'm sort of defining this using a lot of text. There's another video where I use a PowerPoint to sort of illustrate these concepts. I highly recommend that you watch that video in addition to this as well. In fact, if you haven't seen it yet, you should go back and watch the other one first. Okay. So let's look at a little bit of function notation here. And for example, if I give you this function, f of x is equal to 2x squared plus 3x, and I ask you to find f of negative x. Okay? And I think it's best to illustrate function notation with just this example. And so what this basically means is to substitute negative x for x. So to substitute, I just rewrite this entire function, and I just replace all of the x's with parentheses, and then I can substitute in negative x. And sometimes this will make a difference, and sometimes it won't do anything at all to the function. So let's see what happens here. Well, I still get the 2. Negative x squared is just x squared, and I'll illustrate on the side here. So negative x squared is just negative x times negative x. The two negatives will cancel, give you a positive, and you just end up with x squared. Okay? But so here it doesn't do anything, but for this part it becomes negative 3x. Okay, so this is f of negative x. Okay? Let's try one more example. Let's try to find f or negative f of x. So the issue is, what do we do when there's just this negative in front of the function there? And the rule for that is we just copy the entire original function, and then we multiply the entire thing by negative 1. So take that entire thing and just multiply it by negative 1. Okay? And it turns out that you're going to get negative 2x squared minus 3x. Okay? So you can see a little bit of similarities and differences here in the way we approach this. And later in the lesson, when we talk about function symmetry, these concepts will come back a little bit more. And there's actually a lot more that we can do with function notation, but for today's lesson, that's as far as we're going to get. Now, every function has a domain. And the domain is the set of all valid inputs into a function. So if you can substitute it into a function and get one valid output, that's part of the domain. The range is the set of all possible outputs of a function. Okay. So for example, if I had this function right here, 1, 3, 8, 7, it maps to 6, this one maps to negative 5, this one also maps to negative 5, and this one maps to 10. Okay. So this is all of the inputs. This is all of the outputs. So the domain here would be 1, 3, 8, and 7. And then the range would be 10, 6, and -5. All the possible inputs, or the possible valid inputs, and all the possible valid outputs. Now this is a very simple function. It's a finite function. So it's going to get much more challenging when we start to deal with infinite domain, infinite range. But this is sort of a basic example to illustrate the idea. So before we go on to working on domain and range of a function, I've defined here what's called vertical asymptotes. Okay. Now intuitively, vertical asymptotes mean that if you have a graph and the graph looks kind of like this, so this is y, this right here is x, and then you have something like this. And this is f of x, whatever that equation is. This is the graph for it, f of x. Oops, let me draw this better here. F of x. Okay. There's kind of an imaginary line here that the function gets closer and closer to, but never quite touches. And so this is sort of the geometric or the graphical intuition for it. But what I have up here is the more rigorous definition. And that's the definition that we really have to work with when we're working in something in pre-calculus or calculus. So let me sort of just demystify the notation here. So what this part right here, it means this x here, arrow A, and then minus, it means as x approaches A. Okay? So as x approaches A, f of x goes towards infinity. This says as x approaches A, I'm sorry, this with the minus sign here, it means from the left. So going right, coming from the left. Okay. This notation here, right, let me use a different color here. This right here means as x approaches A from the right. Okay. So basically it says that as x approaches A from the left, f of x, or the function itself, goes towards infinity, or it could go towards negative infinity from the left. So let's look at here. I stand on the function and I walk from the left, so going right, and as x gets closer and closer, let's say this line here is A, whatever this is right here. As I get closer and closer to A, the y values decrease to negative infinity. Same thing on this side. As I approach it from the right, it goes closer and closer to positive infinity. Okay? And in this case, then x equals A is the vertical asymptote. And notice I didn't say anything about crossing over the line, touching the line. That is not part of the definition. That works most of the time, but it is not part of the definition. And there are some very tricky counter examples for that. And so you might see a lot of textbooks just sort of condense these two ideas together, and they'll say the limit as x approaches A from the left of f of x is equal to plus or minus infinity. And they'll do the same thing here. The limit as x approaches A from the right is also plus or minus infinity. Okay? And so that's the idea behind an asymptote. And let me show you a couple of other examples. Let's look at, this is kind of a weird looking graph, but let's say I had my axes, okay, and then I had sort of an imaginary line right here, and then I had a graph that does something like this, okay, and then from here it does something weird like that. So here, this is highly unusual because you have the graph that actually crosses over this imaginary line, but it is still an asymptote. The line itself is still an asymptote because it meets this description. As you approach from the left, the graph goes towards positive infinity. Okay? And that's the most important part about the definition, is that it goes towards positive infinity or negative infinity as x gets closer and closer to a. It's got nothing to do, it's allowed to cross over at least some part of the graph is allowed to cross over the asymptote. As long as one part of it satisfies one of these definitions, then the vertical line is in fact a vertical asymptote. So I'm going to end this video right here and then continue on the rest of the notes for finding domain and range and vertical asymptotes on the next video.